Every time you board an airplane, you're stepping into one of the most carefully engineered machines ever built. It may look simple from the outside, just wings, a body, and a tail, but every single part has a specific job. And when even one of them fails, the consequences can be catastrophic. In the next 10 minutes, we'll break down the basic parts of an airplane, explain what they do, and show you what happens when things go terribly wrong. Because understanding these machines isn't just fascinating, it's a matter of life and death for everyone on board. Let's start with the fuselage, the main body of the airplane. This is where passengers sit, cargo is stored, and the cockpit is located. Think of it as the airplane's backbone, the structure that holds everything together. The fuselage is designed to be strong enough to handle extreme pressure changes, violent turbulence, and thousands of hours in the air. But what happens when it fails? In 1988, Aloha Airlines Flight 243 was cruising at 24,000 feet when a massive section of the fuselage's roof suddenly tore away. The metal skin had weakened from years of pressurization cycles, and in an instant, passengers were exposed to the open sky at nearly 5 miles above the ocean. The explosive decompression was so violent that one flight attendant was sucked out of the aircraft and never found. The pilots managed to land the crippled plane, but that incident showed the world just how critical the fuselage's structural integrity really is. Every rivet, every seam, every panel must be perfect, because at altitude, the pressure difference between inside and outside the cabin is immense. One weakness, one crack, and the entire structure can catastrophically fail. Now, let's talk about the wings, because these are what make flight possible in the first place. Their curved shape, called an airfoil, allows air to move faster over the top surface and underneath, creating a pressure difference that generates lift. Without wings, an airplane would be nothing more than a heavy metal tube that could never leave the ground. Wings also store fuel in many aircraft, making them serve double duty as both lift generators and fuel tanks. But wings are under enormous stress during flight. They're constantly flexing, bending, and absorbing forces that would snap most materials in half. You probably noticed during turbulence how much the wings can bend, sometimes visibly moving up and down by several feet. That's actually by design. The flexibility prevents them from snapping. But there are limits. In 1954, two de Havilland Comet aircraft disintegrated in midair, killing everyone aboard. Investigators discovered that metal fatigue around the windows had caused the fuselage to fail, but also highlighted how wings can suffer similar stress fractures. More recently, engine failures have caused debris to puncture wings, leading to fuel leaks and fires. Imagine being a passenger watching flames erupt from the wing outside your window, knowing that if the fire reaches the fuel tanks or if the wing structure weakens too much, the entire wing could separate from the aircraft. That's not Hollywood drama. That's happened in real accidents. The wings aren't just important, they're everything. Without them functioning perfectly, there is no flight, only a long, terrifying fall. Attached to the wings are smaller moving parts called ailerons and flaps, and these are the control surfaces that give pilots the ability to maneuver the aircraft. Ailerons are those panels on the outer trailing edge of the wings that move up and down to make the airplane roll left or right, especially during turns. When you want to turn left, the left aileron goes up, reducing lift on that wing, while the right aileron goes down, increasing lift. This creates the banking motion you feel during turns. Flaps, on the other hand, extend during takeoff and landing to increase the wing surface area and change its shape, allowing for more lift at slower speeds. If you've ever noticed the wings changing shape dramatically while landing, becoming larger and more curved, that's the flaps deploying. But what happens when these control surfaces fail or get damaged? In some cases, pilots have lost control of ailerons due to hydraulic failures, making it nearly impossible to keep the wings level. They've had to use rudder and engine thrust differentials just to keep the plane somewhat controllable, essentially trying to fly a machine that no longer wants to respond to normal inputs. In other cases, flaps have failed to deploy symmetrically, meaning one wing gets more lift than the other during landing, causing the aircraft to roll violently to one side just feet above the runway. Pilots have seconds to react, often having to abort the landing and circle back while trying to troubleshoot the problem. And in the worst scenarios, control surfaces have been damaged by bird strikes, hail, or mechanical failure, leaving huge chunks missing or stuck in dangerous positions. Flying an airplane without proper aileron or flap control is like trying to steer a car where the steering wheel only sometimes works. The fear in the cockpit during these moments is unimaginable. The engines are the heart of the aircraft, providing the thrust that pushes it forward through the sky. On jet aircraft, engines work by sucking an enormous amount of air, compressing it to incredibly high pressures, mixing it with fuel, and then igniting it to create a controlled explosion that blasts out the back, generating forward motion. The faster the airplane moves, the more lift the wings generate, and everything works in perfect harmony. Modern jet engines are marvels of engineering, spinning at thousands of revolutions per minute, operating at temperatures that would melt most metals, and doing it all reliably for tens of thousands of hours. But when an engine fails, the situation becomes immediately life-threatening. Engine failures can happen for many reasons: bird strikes, mechanical breakdowns, fuel starvation, or ice ingestion. When an engine explodes, and yes, they can literally explode, pieces of turbine blades can shoot out like shrapnel, puncturing the fuselage, severing hydraulic lines, or even hitting other engines. In 2010, Qantas Flight 32 suffered an uncontained engine failure, where an entire turbine disc exploded, sending debris through the wing and knocking out multiple critical systems. The pilots faced a cascade of failures, and only their skill and the aircraft's redundant systems prevented a total disaster. But imagine being a passenger on that flight, hearing the massive explosion, feeling the aircraft shudder, and then watching as alarms fill the cockpit and the pilots worked frantically to keep control. Engine failures at low altitude, during takeoff or landing, are even more dangerous because there's no time or space to recover. Pilots train for engine-out scenarios constantly, but when it happens for real, with hundreds of lives depending on split-second decisions, the pressure is unimaginable. And if all engines fail, well, you're in a glider that weighs hundreds of thousands of pounds, and you have only minutes to find somewhere, anywhere, to put it down before you run out of altitude. At the back of the airplane is the tail section, also called the empennage, and it includes the vertical stabilizer and horizontal stabilizers. These parts keep the airplane stable and pointing in the right direction, controlling pitch, which is the nose-up or nose-down angle, and yaw, which is the left-right direction the nose points. Without the tail, an airplane would be aerodynamically unstable, spinning and tumbling to the sky with no way to maintain controlled flight. The tail is essentially what keeps everything flying straight and true. But when the tail fails, the results are almost always catastrophic. In 2001, American Airlines Flight 587 crashed in New York after the entire vertical stabilizer, the tall fin in the back, separated from the aircraft during flight. The plane immediately became uncontrollable, rolling and pitching wildly before slamming into ground, killing everyone aboard and people on the ground. The investigation revealed that excessive rudder inputs had overstressed the attachment points, but the fact remains, without that vertical stabilizer, the pilots had zero chance of recovery. There have been other cases where tail strikes during takeoff, when the rear of the aircraft scrapes the runway, have caused hidden structural damage that weaken the tail over time. Years later, that damage can lead to sudden, catastrophic failure at altitude. The tail may look like just an afterthought, a small structure at the back, but it's absolutely critical. Losing it means losing all control. And at that point, you're not flying anymore. You just fall with style until you hit the ground. Attached to the tail are the rudder and elevators, the moving control surfaces that pilots use constantly to maintain smooth, stable flight. The rudder is the vertical panel on the back of the vertical stabilizer, and it controls yaw, pushing the nose left or right. The elevators are the horizontal panels on the horizontal stabilizers, and they control pitch, tilting the nose up or down. Pilots use these controls in coordination with the ailerons on the wings to execute turns, climbs, descents, and every other maneuver. Most passengers never even notice these surfaces moving because modern autopilot systems and skilled pilots make everything feel smooth and effortless. But when rudders or elevators jam, fail, or become damaged, the aircraft can become nearly unflyable. There have been cases where rudder hardovers, where the rudder suddenly slams to full deflection and gets stuck there, have caused planes to roll uncontrollably and crash. Pilots have fought against jammed elevators, trying to use engine thrust and trim tabs just to maintain some semblance of control over the aircraft's pitch. In combat and severe weather situations, control surfaces have been torn off entirely, leaving pilots with only partial control authority. Flying in these conditions requires every bit of skill and nerve a pilot possesses, and even then, survival is far from guaranteed. The mental and physical strain of fighting a crippled aircraft, knowing that one wrong move could send everyone into an unrecoverable dive or stall, is something nightmares are made of. The landing gear is what supports the airplane during takeoff, landing, and while taxiing on the ground. It absorbs the tremendous impact forces of landing, which can be equivalent to dropping the aircraft from several feet onto concrete, and it allows the aircraft to slow down safely using brakes and, on some aircraft, thrust reversers. Once airborne, the landing gear usually retracts into fuselage or wings to reduce drag and improve fuel efficiency. The gear seems simple, just wheels and struts, but it's actually a complex system of hydraulics, actuators, locks, and sensors. And when landing gear fails, pilots face one of the most terrifying scenarios in aviation.